trig form of a complex number. Okay, so again, trig, that's like sines and cosines. Complex number, that's like 7 plus 3i. So you've done plenty of sines and cosine things. You've done plenty of complex number things, but there's this way where they match up, and that's what this unit is about. In fact, the intersection of those two things is this unit, not just today, but this whole unit. So let's rehash a little bit of complex number stuff. Imaginary I is defined as the square root of negative 1. Right? You remember that? So that the square root of negative 25 is 5i. That's old news, I hope. A complex number in standard form is written as a plus bi. Right? And usually it's not a's and b's. Usually there's numbers there, like 3 minus 5i or whatever. That's a complex number. Because it has a real part, a, the number without the I on it, and it has an imaginary part, b, the coefficient of I is the imaginary part. A number of the form bi, where b isn't 0, is called a pure imaginary number, meaning there's not a real part to it. So if we had 3 minus 5i and we took off the 3 and we just had negative 5i, that would be a pure imaginary number because it's only imaginary. There's no real part to it. The set of real numbers is a subset of the set of complex numbers, because real numbers would be the a parts. You could also say the set of pure imaginary numbers is a subset of the complex numbers. Because, a could be written, if b is 0, then a plus bi just turns into a. Right? A plus bi equals a if b equals 0. So, real numbers you can still think of as complex numbers, they just don't have the imaginary part with them. Okay, this is where things get a little interesting. We can graph complex numbers on the complex plane. So usually we're thinking x and y. And this works almost the same way, but instead of x and y, our axes are real and imaginary. Have y'all done that? Have you graphed numbers on the complex plane before?
Yes.
Okay. Some yes, some no. It's really easy to do, as long as you remember that the real part is the x-axis and the imaginary part is the y-axis. So that negative 5 plus 8i means the real part is negative 5, the imaginary part is 8. So if we graph negative 5 plus 8i, there's where it lands. If we graph negative 7i, how am I going to graph that? Where's that going to be? Yeah, just go down 7, right there, for negative 7i. So graphing is pretty easy. It works just like x and y. Just remember the real is the left-right axis and the imaginary is the up and down axis. Graph 8 plus 6i on the complex plane provided. Okay, so over 8 and up 6. Over 8 and up 6. Find the distance between the origin and that point. There's the origin, there's that point. So I want that distance. Well, if I sketch in a triangle there, I hope it becomes obvious how to find that distance. A squared plus b squared. 8 squared plus 6 squared. 64 and 36 is 100. So that distance would be 10.
So does the
matter that one of them is imaginary?
It does not matter that one of them's imaginary, because if we're talking distances, we don't care about the I part of it. So yeah, I guess be careful. You don't want to plug in 6i and square it and get negative, because we're just talking about distances. Now, this is maybe a little bit weird. The distance is also called the absolute value of 8 plus 6i. Okay, so absolute value, and this, if we had taught absolute value this way from the start, this would make more sense. Like, instead, we teach it as it's always just make it positive. But what we should have said is absolute value is how far is negative 3 from the origin. Like, well, let's graph it out. Oh yeah, it's 3 away from the origin. So if you define absolute value as distance from the origin, then it's consistent across everything. The trouble is we didn't really define it that way. Usually we just say, oh, it makes things positive. And then that's a little bit weird when you get to absolute value of negative 3 plus 4i. So without graphing that, can you figure out what the absolute value of negative 3 plus 4i would be? I picked some values that should work for you. Yeah, it's 5. Because you'd go left 3 and up 4. That makes a 3, 4, 5 triangle. So this is a little bit weird. If your brain has in it that absolute value means make it positive, that works for real numbers. That doesn't really work for complex numbers. So you kind of have to adjust your brain on what absolute value means. Instead, think of it as distance from 0 or distance from origin. And so it still works for easy numbers, but now it works for complex numbers as well. Okay, well, here it is in a box, what we already said. The absolute value of a complex number is defined as the distance between the origin and the point. So it's always a squared plus b squared equals c squared. And here's another word that means the same thing, modulus. I don't know that we'll use that word very often, unless you get, that's like higher level math stuff. But modulus is the same thing. How far are you from the origin? So determine the value of the absolute value of z, or the modulus of z, or the distance of z from the origin, given negative 6 plus 4i. Well, you don't even need it. I mean, you can graph it if you want, but it's just going to be the square root of 6 squared plus 4 squared. So that would be 52. But 52 is 4 times 13. So 2 square root 13. In calculus, you get to stop here, but in pre-cal, we have to simplify. So stay tuned. Next year, we get to do a lot of these kind of things where all those times you missed 2 points for simplifying, you don't have to worry about it next year in calculus. But that's next year, so don't leave it at this just yet. Okay, last semester we did some basic stuff. We add, subtract, multiply, and divide with complex numbers. So let's do that. That should be pretty easy. Certainly the adding and subtracting ones are not difficult. Yeah, that's what we need. Let's see. This is third period. Third period box go. We can pick on some helpers here. Certainly for 4 and 5. And we'll do the others together. Andrew, number 4, what you get for? Good. Yep, it's just like collecting like terms. So add the real parts, add the imaginary parts, -5 minus 6i. Victoria, a little bit more complicated. Be careful with the minus sign.
-11 plus 8i.
-11 plus 8i. So just, again, careful with the minus sign. I'm not going to pull somebody for number 6 because it's a little more complicated, but what's the process here for number 6? Foil. So first, outside, let's see, 18i, inside plus 10i, and last, and here's where I got to be real careful, -30i squared. But I squared is equal to -1. So this becomes plus 30, and minus 6 is 24, and then 18i plus 10i is 28i. How do we do number 7? Because it's not, I mean, it's a division problem, but we don't work it as a division problem.
You multiply the top and bottom by
You multiply top and bottom by 1 plus 5i. If you tried minus, it wouldn't work, and hopefully you'd figure out that 1 plus would be a better way to go. So multiply top and bottom by the conjugate. That should make the I stuff go away, in the bottom anyway. So more foiling. First, outside, inside, and last, I'm going to get brave and try to handle the I squared on the fly here. So 15I squared would be minus 15. While I'm working on the top, I'm going to stay there, and then I'll come back and clean up the bottom. So -19 minus 17i. And then in the bottom, first, outside and inside go away. That's why we multiply by a conjugate. The outside and inside always cancel each other out. Minus 25i squared, which means plus 25. So 26. This isn't wrong, but when we do complex numbers, we almost always split up the pieces. I wouldn't take off for the first answer, so I'll box it as in it's acceptable. But you will almost always see it split up. And I think the reason is, or at least one of the reasons is, in other applications, like I know in electrical engineering, the real part means something and the imaginary part means something. So it's easier if you just split them up, so it's easy to say, well, this negative 1926 is the blah, 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 and negative 17 over 26, that's the other thing. And that's how much I remember from my electrical engineering class long ago. What if we were asked to find the value of -2 plus 4i to the 6th? Yeah, you could use Pascal's. That would be at least a better way than what I'm about to write out. I'm not going to do it. But you're right. The Pascal's triangle stuff would be helpful. Would be better than. All right, I'm not writing it anymore. Would be easier than doing that. So yeah, Pascal's would be nice. The triangle thing. It'd still be annoying, right? Because you have to keep up with the i's to some weird power and keeping track of all the coefficients and yeah, long but possible. Yeah, long but difficult. On the other hand, what if we were asked to find the 5th root of 2 plus 3i? Let's just go with a bunch of question marks on that one, because we don't know how to do that yet. You could put it in the calculator, and it would give you an answer. but we'll find a different way later. And that's what's kind of cool, unique, weird about this that's coming. But that's in this unit, we're able to do stuff like that and do it relatively easily compared to what you think might be the process. So that's what's coming. For now, powers and roots of complex numbers, it's helpful to write them in trig form. So we've got to learn how to put them in trig form, and then we can answer these questions a whole lot easier. Okay, so back to basic trig stuff. Cosine, let's see, SOHCAHTOA, going all the way back to like geometry here. Cosine is adjacent over hypotenuse. So that means A would be R cosine theta. I'm rebuilding it from scratch here. Eventually, you're not going to have to do this, but it's kind of building it up. Sine is opposite over hypotenuse, so B over R. So B is R sine theta. Okay, now here's the connection between trig and complex numbers. A plus BI, well, A is R cosine theta. And B is R sine theta. Let's be careful, make sure the I goes to the whole thing. It's not like theta times I. There's no imaginary angles that I know of anyway. And so how we usually write that is factor the R out. Cosine theta plus I sine theta. Move the I in front because it just looks a little better. Okay, but then we need to think about what R is. Well, R is A squared plus B squared equals R squared. So the square root of A squared plus B squared. To kind of tie it to what we did earlier, that's also the distance from the origin, or the absolute value of A plus BI, or the modulus, if you want to sound really fancy. Tangent of theta is opposite over adjacent, is B over A. Okay, so today what we're mostly going to do is go back and forth between A plus BI and R cosine theta plus I sine theta. Okay, so this box is really what we just kind of explained right there. So there's nothing new in the box. The box just tries to simplify it and put it in the box to make sure you understand that that's important. A lot of times we'll say Z to represent a complex number. So A plus BI can be written as R times cosine theta plus I sine theta, as long as we understand what all those pieces are and how to get them. But most people don't memorize that. They use it enough where they get it, and if they get stuck, then it just takes a really quick picture to make all the connections of A and B and R and theta. And so, again, it's not something you have to specifically memorize. You use it enough to figure it out, and if you do get stuck, you redraw the quick picture and kind of build it back from scratch if you need to. We saw this once before in a bonus this year. R times cosine theta plus I sine theta is commonly abbreviated as R cis theta. It's pronounced cis, like sister. R cis theta. It's just a shorter way to write it. Number 8, write 8 cis pi over 6, I'll even say it, in standard form. So standard form means I need A plus BI stuff. So 8 times, let's see, cosine pi over 6,
Oh, let's pick on people. Force you to think about the unit circle.
Cadence and Rebecca. Oh, that's right. Victoria points out that once Cadence gives her answer, Rebecca will know that it's just the other one. So, Cadence, put us on the right track here. What's cosine of pi over 6?
Square root of 2.
Yes. So, Rebecca, even if you didn't know the sine of pi over 6 before, hopefully you know it now. 1/2. I'm going to assume that you knew it before. You will neither confirm nor deny if that's correct or not. So 4 root 3 plus 4i. Number 9, same kind of question, but we've written it in this weird looking form. So probably best to just expand that form out. 5 cosine 5 pi over 4 plus I sine 5 pi over 4. And then it's just another unit circle problem. So I'm going to press pause and let you finish that one.
Negative 5 root 2 over 2. I guess I could have just made that minus 5 root 2 over 2 times I. They're the same, so you could factor it out. But again, we don't like it factored out. We like it written out so that we can easily see the A piece and the B piece of the answer. Again, just because later on, A and B have particular meanings, so we want to be able to quickly identify them. Number 10, go the other way. So start with the rectangular form, and we want to write that in trig form. And to me, the easiest way is to draw a picture of it, because then I'll probably get the angle correct. So negative 3, 3 is right there. So I need an R and a theta. Do you remember your special right triangles well enough to know what R is without having to go through the process of A squared plus B squared equals C squared? So you're like, no. If those two sides are the same, then that it's a 45, 45, 90.
So it's 2 times that?
It's not 2 times that, right? Because if the hypotenuse was 6, then that would be, you couldn't make a triangle. It wouldn't work. 3 root 2. Again, if you need to, and sometimes you have to because the numbers aren't nice, but if you need to, you can go through the whole, what would that be? 18, square root of 18 is 3 root 2. But usually we give you ones that you should recognize and makes your life a little quicker, a little easier. Speaking of a little quicker and a little easier, I can work through the process of inverse tangent, but I could also think, wait a minute, if that's a 45, 45, 90, what's the middle angle in the second quadrant? What angle is that? 3 pi over 4. And again, to go the long way, you'd say, well, tangent of theta is b over a, which is 3 over negative 3, which is negative 1. So you know it's over. But don't do all that. Like, look at the picture. Theta is 3 pi over 4. So if I've got r and I've got theta, then I can write my answer as 3 root 2 cis 3 pi over 4. Again, 8 and 9 were a plus bi into r cis theta. 10 and 11 are r, whoops, other way around, are a plus bi into r cis theta. So just going back and forth between the two of them, or the two forms. Like last time, I'm going to pause. You try number 11. So there's my r, there's my theta. So 2 root 3 cis 4 pi over 3. get a little bit of a graphical confirmation. 4 pi over 3 is the angle. 2 root 3 is the distance. And so we've now got it in trig format rather than algebra format, a plus bi. All right, number 12. Number 12 was similar to that bonus you had on that test a few tests back.
10, let's see, cis 5 pi over 6. So that's cosine 5 pi over 6 plus I sine 5 pi over 6. Cis 4 pi over 3, cosine 4 pi over 3 plus I sine 4 pi over 3.
And so I've got, 4 trig questions there, and then a FOIL, and then a distribute. So it's a lot of little pieces, but it's little pieces that hopefully we know.
Let's see, 5 pi over 6, that's over there. So that would be negative root 3 over 2 plus I times a half.
4 pi over 3. Again, maybe you don't have to draw the picture, but it really helps my brain to get them right and get the signs right if I can look at it.
Cosine's clearly negative 1/2 plus sine would be negative root 3 over 2.
Let's hold off on the 10. Let's FOIL things first, and then we'll distribute that 10.
First would be positive root 3 over 4. Outside is going to be positive 3/4 I.
Yeah, negative times negative, root 3 times root 3, 2 times 2.
Inside would be minus 1/4 I.
And last, we got to always be super careful because I squared is negative 1.
It's like, how much do you want to do at once? Root 3 over 4. Is it going to be positive or negative? Positive, because the negative, but then I squared is negative, so positive root 3 over 4. Still holding off on the 10 here. Root 3 over 4 plus root 3 over 4 would be 2 root 3 over 4, or root 3 over 2. 3/4 minus 1/4 would be 2/4, or 1/2. And then distribute the 10. So 5 root 3 plus 5i.
And it wanted that in reduced standard form. So reduced, no fractions, standard form meaning a plus bi, which we got. Okay, so again,
The vast majority of today is going back and forth between a plus bi and r cis theta.
and to me, if you draw a picture of either one, it helps you figure out how to get back and forth. So rather than memorizing, a squared plus b squared and inverse tangents, just draw a picture and use the picture to help you go whichever way you need to go.